So Saturday, the 25th, we're gonna, please make sure to write down in your notebook the notes on this so you can, add volume and try to show evidence of hard work. So anyways, we're going over Hardy-Weinberg practice problems, and then we're gonna go over the chi-square practice problems, and the whole point is that on Monday you have this quiz. I'll be uploading the video just so people know what we covered on Saturday. All right. So the first one that you see is they talk about allele frequencies, and then there's recessive traits, and then there's this idea of genotypic frequencies. So there's a real kind of misunderstanding, I think, that's prevalent, and that's number one, the difference between allele frequency and this idea of hold on a second, and your genotypic frequencies. When you have P plus Q equals 1, that is talking about the frequency of the allele in a pool. If you have a pool, a population, and you have two alleles in that population, okay, and those alleles can be big A, and then the other allele can be little a, for instance. So there's this pool of genes. These are the pool of alleles in that population. That's what this represents. So if you know the allele frequency of one, if you know the allele frequency of one of the two, then by definition you know the other. Do you understand that? Is that clear?
Yes.
That's why it equals 1. Does that make it? Yes or no? Does that make sense? Okay. So if I tell you have 0.5 p, then what must q be? 0.5, whatever's left of the pi. So think of this pool as, you can think of this pool as a pi, or as what we say, a pool, a gene pool, and whatever's in there is 100%. Instead of putting 100% in the equation, we just put 1, right? And so if 50% are p, then the other 50% must be q, because that's the only other option. Right? So that's kind of really a fundamental idea. If you can't understand that, then you can't understand anything else. And if you understand that, some of you are sitting there, I can tell, you're just like, I get that. That's not the problem. No, that is the problem. The problem is you don't apply that. And it's the Hardy-Weinberg is just simply an application of that. Now this is just the frequency of the one allele. When we're talking about genomic frequency or genotypic frequencies, what we want to talk about is p squared. And then you talk about 2pq, and then q squared. And then that also is going to equal 1. But only, and by the way, all these two equations, and this is going to be key, this is only true, right? These are only true when evolution is not occurring. All right, so what do we call that when we say something's not happening? What kind of hypothesis? The null hypothesis. So this is the null hypothesis. So it's only when the null hypothesis is true do we say that this is occurring. So when is what's the opposite of the null hypothesis? The alternative hypothesis. So if we reject the null hypothesis, then we have to accept the alternative hypothesis. And the alternative hypothesis is what? Evolution is occurring. Does that make sense? How do we define evolution? That's right. Who said that? That's right. The change in gene frequencies. if you change the allele frequency over time, the population was going to change. We all agree on that, and we can see it happen. All right, so when we're talking about the null hypothesis, if this is all true, if the null hypothesis is true, if we have evolution going on, then none of this works out. So if you do this equation and somebody gives you a bunch of data and you do it and it doesn't work out, p squared plus 2p cubed plus q squared does not equal 1. Assuming you did the math right, then what do you think is happening? The null hypothesis is rejected. You have to accept the alternative, which is that there's something going on. And what happens is you have this idea that evolution is occurring. What do we define as the kind of the premise, those 5 premises that we discussed? Large population. So when you have a large, this is for the null hypothesis to be true, right? The large hypothesis.
No immigration or neither.
Right? No immigration. That is, and immigration. But understand, when she says sexual selection, it's no sexual selection. Right?
Should large hypothesis be large population?
Yeah. I'm trying to do 3 things at once and it never works out. Don't ever, I don't know why I keep trying. And it's bad for you too, it turns out. Large population. Large population, no immigration, no sexual selection, no mutations. No gene flow. Well, sorry. That's true, but no gene, this is gene flow. Right? What's the one that's missing? No natural selection. And we all understand what natural selection is? What is it?
When there's no human interference or involvement.
Okay, so that's what the natural means. I agree with this statement. Did you hear his statement?
It's when people or other things are involved in the killing of things.
Okay, so that's the natural part. But selection just means no. When you talk about natural selection,
It happens without involvement.
yeah, without human involvement. That's right. That's the natural part. No human involvement is no human involvement. So when a dog breeder, something is artificial selection. And the truth is that for evolution not to occur, there can be no selection at all. See, artificial selection also will cause evolution. And you have who has dogs in this room, or has friends that have dogs? Then you know about artificial selection. Each of you has a breed of dog. That breed of dog is different only because humans decided to select them. You got a pit bull that has a head this big because people bred dogs with bigger and bigger heads. I got a dog with a big head, I'm only going to let him breed with a dog with a big head. And if you look at all breeds of dogs are the result of artificial selection. But it's still evolved. They still evolved, right? The population's changed. So artificial selection is when humans are involved. And one prime example of that I think I've repeated a couple of times is dog breeding. And it's not necessarily that they're bigger and stronger, because somebody bred a Chihuahua, and those are tiny little things. Each dog was bred for a different purpose. But in natural selection, it's just that nature, not humans, but nature, decide that some trait is beneficial. All right, so nature decides. And how does nature decide? Through disease, through some event, something, the human population, humans coming out of Africa, out of East Africa, moving north, right, into the northern lands. Less sunlight. We evolved to be lighter colored. So the population that did move north became lighter over thousands and thousands of years. So that would be an example of amount of sunlight on someone was an example of selection. The people that were darker up north died earlier, before they could have babies. So, and over time, you have this idea of natural selection. So natural selection is death before birth, reproduction. So that's another key part of natural selection. The thing has to die before it has babies. If it has babies, it's too late. You might ask, how come men and women have heart attacks? Why do we die so at 40 and 50 years old, 60 years old, 70 years old, right, with heart attacks? Why have we evolved over time to die so what we consider early, right? How does that happen? Well, natural selection can't impact that. Why can't natural selection impact something that's going to kill you at 40 and 50 and 60 years old? Exactly right. By that time, you already have babies. So that gene is not leaving the population. Do you see what I'm saying? So I'm glad that you say you don't. Look, how do you go from, if you got this thing, right, let's say gene little a. If you have this gene little a, let's not even call it little a, let's say little a, okay? If you have that genotype, you die at 40, 50, 60 years old, some heart attack. It's going to kill you. 99% of the time, it's going to kill you if you have that gene. Breast cancer is another example, right? Angelina Jolie found out she had a really aggressive version of breast cancer. She had her breast removed. Another example is ovarian cancer. So some of these things, all the cancers generally happen when people are older. So let's say it doesn't matter what the disease is. So let's say you have a disease that kills you when you're 40 or 50. You have babies. You have 3 babies. What genes did you give that baby? One little a, right? And if the husband had a little a, then they have little a, little a. Will that ever leave the population when they have? Because that's not going to kill you until you're 40. But you probably have babies at, in today's society, 18, 19, 20, maybe 30, right? If it kills you at 40, you probably already had babies. After you have babies, natural selection can only work to get rid of that gene in the population if they killed you when you were 16, 15, 14, before you had babies. Because then the genes don't get passed on to the next generation. So the idea, that's why sickle cell, if you watch that video and think about it, that's why sickle cell is in the African American population in such high percentages. Because the heterozygote is favored. And because people have babies. If you have babies with the trait, then the trait stays in the population. The only way the trait leaves the population is if the people with it die before they have babies. Does that make sense? So that's death before. And also the other thing about natural selection is that it's selecting one trait over the other. So in order for natural selection to make a difference, it would have to decide, big A, if you have big A, you die. If you have little a, you live. Then what's going to happen? Before you have babies, what's going to happen over in 1,000 years? They leave the population. That gene would leave the population. Anybody with that gene is going to die, so they're gone. And we used a moth example, and we had the idea that, look, if you got this area that's all black, like what happened during the Industrial Revolution in England, and you have this butterfly, and it was a moth actually, but this moth that had, that was white. And so to have that, you had to have little a. Then you had a moth that was black. And I can't draw a black moth, but we'll do that. All right, yeah, black moth, I just outlined it in white. And then you had a moth that's is what?
You said, oh, like black and white.
Yeah, both. Yeah, like little dots, right? So a spotted black moth, right? So which moth? This. So if this is big A, little a, and this is big A, so it's codominance, right? So maybe I shouldn't put little.
Big A.
Oh yeah, sorry. But let's say that this is the situation. Which of these moths is going to die first? Before it even has a chance to have babies, right? Because the hawks and the owls are going to come in and swoop in and take them out. And so which one of these is going to have babies? The big A is going to have babies for sure, right? So if the big A is having babies, then it survives. It sends its what genes is it sending into the next population? Big A. So it's a lot of big A's going in the next population. The spotted moth might survive better than the white one, but it's going to survive worse than the big one. So more big A's are going to have sex with each other, have babies, right? So the little A is still in there somewhere, right? It kind of hangs out, and because you have that spotted out, because of that heterozygote, it kind of hangs out, so it survives a little bit. But still, I'm gonna put a little red X on it because still it dies to some extent more often than the big A. But the result of it, assuming that this is all happening before they have babies, what's the result?
Black population.
An increase, and I'm going to go ahead and write that down because I like that. An increase in black moth population. But what does that mean for the allele frequencies? An increase in what? An increase in big A's. I said allele frequencies. And the increase in black population means what? And it really what we're talking about is an increase in big A, right? Or P squared, right? And an increase in big A means an increase in P, right? Do you agree?
Yeah, and then the decrease
Increase in P. And because you're getting rid of all the homozygous recessives and even a lot of the big A, little A's, what you're getting is a decrease in the little a or a decrease in Q. All right, remember that means because that happens because Q squared's coming down. Do you see how that works? So that's natural selection. That wasn't humans doing that, right? That's the owl or the eagle or whatever coming in and eating the butterfly. Hey, how you doing? Some donuts, guys. Let's take a break. Get your donuts and let's sit down again. So here they give you the alleles, and over here they're asking for genotypic frequencies. One other thing that people keep forgetting that some people that stayed after school yesterday, we were talking about it, is how do you calculate the frequency? See, frequency is something that really people get confused about. They think that the number you have, if you have five individuals that have big A, that's your genetic frequency? No, it's all about how many are in the population. So you have to have the total population number. So anyways, unless you're given allele frequency. See here, this is an allelic frequency. They gave you that. They told you that. So that means it's 0.9 means what? 90% of the alleles in the population are big A. And this means what? 10%. That's right. 10% is little a. And remember, this makes sense because you have to have P plus Q has to equal 1 if it's in Hardy-Weinberg, and 0.9 plus 0.1 does equal 1. So we're good. So now, genotypic frequency. How am I going to find the genotypic frequency? Well, that's easy. I know that P squared is a big A frequency, and that's gonna equal 0.9 squared. No, the square root comes in later. See, it's confusing. You have to know when to use square root and when to use square. And it's easy to confuse them, right? But when you're trying to find the genotypic frequency, you're trying to find how many in the population have double A's, you have to square it. You have to take P, which is the A frequency, and square it. So then you have, what am I doing? Then you have big A, little a is going to equal 2PQ, which is going to be equal to 2 times 0.9 times 0.1, whatever that number equals.
81.
And then little a is going to be equal to Q squared, which is equal to 0.1 squared. And that's easy. So you see how easy that is? So if you do the math, you can, somebody have a calculator out? You want to do the math? Do the math. See if you can do it. Huh?
My dad took my phone.
You said what?
My dad took my phone.
Oh.
No, she not 49.
0.9 squared is 0.81.
0.81.
And then 2.9, blah, blah, what is?
0.18.
Yeah, 0.18.
0.18. And then 1 squared is equal to, 0.1 squared is equal to 0.01. And that's your frequencies. Those are your frequencies of your allele. So you got 81% of the population is big A, 18% is heterozygous, and only 1% is homozygous recessive. So given that information, which of the alleles do you think is favored?
The big A.
The big A looks to me like it's pretty favored, don't you think?
Because it's only 1%.
Little a is not favored at all in the population. Given that you're at equilibrium, it seems like that big A would be probably, there's some kind of selection pressures pushing towards this, isn't it? It's kind of, wait 1 second. It's selecting towards that big A allele. Who knows what advantage it has? It could be color, skin color, it could be the heart works better, it could be the liver works better, it could be the brain works better, it could be your eyes work better, it could be your hands work better, whatever. Some advantage is being given to you by that big A. We just don't know in this problem what that is. All right, yeah.
So, you use the square root thing.
Well, we're going to find out because there's a few here that require you to do the square root. Let's go ahead to recessive traits, which...
Oh, I did that.
So allele, number 3 says allele W, and I want to go back and do the one, Lipscomb, the one that you wanted to do that we started last night, and you wanted to go over again. I do have that, and so I want to go over that one
You
again.
got another paper because I need mine back.
You have these done, I'm doing them here. Can you just...
Oh, you are doing the one that's done?
All right, so when you're looking at allele W, and this is the one we were doing last night, Lipscomb. So allele W is white, right?
Right. Oh, that's dominant, so that's equal.
And I'm putting big W, so that means it's dominant.
Little W.
And little w is for, so this, big W blank is going to give you white. Let me go ahead and get rid of this. And little w equals black. And now we're talking about sheep here. Black wool versus white wool. Then they tell you that there's 900 sheep in this sample. So what does that tell you?
That's our total population.
Thank you. That's the total population. That's going to be key. Remember, frequency is how many in that population divided by the total. That's what frequency is. Frequency is how many times does it happen in a population. Does that make sense?
Yeah.
Okay, because it needs to make sense because you have, that's one mistake that's common is people keep like, let me write down what I'm going to write down and I'll show you what I mean. 891 are white and 9 are black. Now, the problem with there's a problem with the white. Does anybody remember what the problem with the white ones are?
You don't know which one.
It could be big W.
That That's right. You don't know which, it could be one, either big W, or big W, little w. So it's not as useful as the black ones, because you know the black ones are what? Little w, you know they're recessive, so you know their genotype. And that's the key. That's the key to one of the keys. There's a couple keys. One of the keys to Hardy-Weinberg is that you're looking for the recessive one. You're looking for the recessive one. Because the recessive one gives you that information. So now what a lot of people would do, and this is going to be a problem for you if you do it, what a lot of people would do is they would say, okay, well, there's 9 blacks, so that tells me automatically, they say, I'm just waiting. I'm waiting for you. I mean, it's really kind of silly that it's a Saturday and I got to deal with this. But nine blacks, so there's 9 little w, so immediately some people are going to say, oh, well, q squared equals 9.
No.
No, that's not right.
You gotta divide it.
Thank you. You have to divide it by the total. So q squared does equal 9 divided by 900. Okay? So again, q squared equals, I'm going to pause for a second. All right, ask it one more time there, Abdul.
It's not just me.
I know it's not just
He
you.
started recording this.
I'm trying to on a Saturday. I'm trying to. I can't answer your question and have all this going on. I can't. That's not how I'm going to work. And it's Saturday and I don't want to have to fight with you. All right, so let me get to your question in just a second. All right? So q squared is equal to 0.01. So what is q squared? 1%.
Yes.
So 1% of the population is little w.
What?
All right? So it's 9 out of 900, 9 out of the total. Now your question, Ms. Lipscomb. What was your question?
I said it was like some with the square root.
Okay, I'm about to get there. I'm about to do it.
Now you gotta do the square root.
Okay, so I'm going to do it. So I'm just trying to get you to...
9 divided by 900, that's 0.01.
That's right. 9 divided by 900 is 0.01. Are we all on the same page now? All right, so that gives us how many little w's you have. That's your genotypic frequency.
But isn't it still squared?
But still, all right, you got to listen to what I'm saying. Just trust me, all right? Just trust me when I say this. This is your genotypic frequency. So what that means is that 0.1% is equal to the frequency of little w, 2 little w's. That's why this is squared.
Wait, question.
Yeah.
So you know how you was like, for the dominant thing, you don't know which one is little W, but if that's all the little W's, then don't that tell you what the big W you got with it?
Okay.
But you wouldn't say
Okay, I hear you. I want to make sure everyone... This one more time. I'm going to repeat it one more time. This q squared just means the frequency of the 2 little w's, of individuals that are homozygous recessive. It does not tell you the frequency of the little w allele. So there's 2 things going on here. You have a gene pool that has a bunch of big W's and little w's running around. All right? And if you want to figure out how many of the little w's and big w's you have, it's not going to help you to know, it is going to help you know the q squared, but q squared does not tell you how many little w's you have. Why doesn't it tell you? If you know how many little people with little w, why don't you know how many little w's there are in the whole population? That's right, you still got heterozygotes out there. So you have to consider that. So you have to in order to find out Q's, in order to find out how many, the frequency of just the little w's, what you do, can anybody tell me, is take the square root. By taking the square root of both sides of the equation, then you're able to to mathematically come up with the frequency Q. And now Q is what? Is 0.1, right? But so Q is, now you have the frequency of your allele. So this is an allelic frequency.
That's the same thing as it was before.
Yeah, but this is your allelic frequency. All right. And it's not what it was before, you see. It's not. Someone just said it was.
Yeah, I did.
Right, see, this is 0.01, this is 0.1. So it used to be 1%. So only 1% of your population, right, is homozygous recessive, but 10% of your population, 10% of all the genes in your gene pool, 10% of this are little w. So where are the other 9%?
Big W.
In your heterozygotes, right?
Right.
All right, so just remember that. Now that being said, let's think about something else that we know. We know something else if we know what the Q is. Once you know Q, then you know something's very interesting. Once you know Q, P plus Q equals 1. So if you're saying 10% of the population is little w, what must the rest of the population be? It must be big W. So 90% of the population is big W. How did I know that? Because 10% is little w. Right?
Right.
I mean, it's just, again, back to that idea that I know is absent in the real world. There is no such thing as common sense. But I'll go ahead and say it's common sense, isn't it? If you have 10% of the population is little w, then 90% must be big W. So let me finish this and I'll let you ask a question. So that tells you 90%. So that's 0.9. 0.9 because it equals what? I hope you can understand equals P. So P equals 0.9, doesn't it?
Yeah.
It is duh, but you say that, but there's going to be people that are going to be confused when they're trying to do it on the quiz on Monday. So your Q is 0.1, your P is 0.9. You know that your allelic, now that you have P, now you can go ahead and say, all right, I know what P is. Now I can go ahead and plug it into the equation. I can find out what P squared is. What is P squared?
No.
What does P squared represent? Let me ask you that question.
The homozygous dominant.
Homozygous dominant. So it'd be big W equals P squared, which equals 0.9 squared. Now that's different from square root. Don't get them confused. Huh? And 0.9 squared is 0.81. So that's your P squared. Now a lot of people, what they're going to try to do, and this is another mistake that I've seen people do that don't do it, is you'll try to take that original number that we calculated up here that says 0.01, and they'll just say, okay, well if Q squared is 0.01, then P squared has to be 0.99. No, because you're forgetting the heterozygotes. You can't do that. So 0.81% are homozygous dominant. Now that you have your homozygous dominant, what's the other one that you can figure out? The other genotypic frequency you can figure out? The heterozygote, which is equal to what? 2 PQs, right? And that equals 2 times what? 0.9 times 0.1. There it is. Just that simple. And go ahead and someone do the math. 2 times 0.9 times 0.1 is 0.18. Right? So that's right. Good. So you see how you saw that automatically, right? You were having a hard time with that. People were having a hard time with that initially. When you see this, you should see 18%. When you see this, you should see 81%. When you see this, you should see 90%, right?
But then don't you say that to get like the actual number, you divide that by total?
What a great question. Now, what if I asked you how many people how many cows? These cows or sheep? How many sheep are black? How many sheep are white? You already know that. It's in part of the answer, right? But if I asked you, if I gave you the genotypic frequency, if I gave you the allelic frequency, I gave you the total population, you should be able to figure out how many black sheep, how many white sheep.
Yeah.
So now, this should work out. You can also use this to check your answer, right? So I should be able to tell how many, I know that the problem tells me I have 9 black sheep. So what that tells me that if I look at q squared, which is 0.01, I should be able to take 0.01 and multiply it, 0.01 and multiply it by, what is the total population? 900. And I should be able to get 9, and I do. So I know I did that math right. See how I can check my answer?
How you check it? What you do?
I took the q squared, which is the frequency of the white sheep population, I multiplied times the total. Now, how come if I take p squared, which is 0.81, and I multiply times 900, how come I get 729? Why don't I get 891? You forgot the heterozygous. So it's 729 plus what? Plus 0.8, plus point what?
1.8
Plus 0.18 times 900
will get you.
equals 162, right? 162.
Add those together.
162.
Wait, what was the last number?
I'll do it right now. 0.81 times 900. I know we don't write things down. That includes me. 729.
Oh.
Add those two together. We should get 891.
6, 7, 8.
And I do. 891. So that's the number. This number was given to me in the problem, wasn't it?
Yeah.
But I could reverse what I got and see if it works out. Then I'm sure that my math is right.
Will there ever
Or
be a
I'm more
time
sure
when,
it is.
you check when like it's just not working, like it's just not what it is, like you can't find the answer. You know what I'm saying?
Is there a time when usually it's a mistake, but sometimes the problem isn't in Hardy Weinberg. Maybe the population is evolving. If the population is evolving, these equations won't work.
Then it won't be Heidi Weinberg because
Right, but the problem tells you it's Hardy Weinberg. So, all right, let's go on to the problem. In corn, yellow corn is governed by dominant allele, white by recessive allele. Random sample of 1,000 kernels. What's 1,000 kernels? Didn't I do this problem already in class?
yes, that's the total population.
So shouldn't we do one that we haven't done in class?
Yeah, like number.
Let's go to number 6.
I don't want to do that one.
So 1 in 7,000 U.S. Caucasian newborns have cystic fibrosis. Big C is dominant over little c, which is for cystic fibrosis. So they gave me a lot of information. They told me little c, big C blank is normal.
Yeah.
And little c is cystic fibrosis. Not a good disease, I'll tell you that.
Yeah.
So anyways, I don't think there is a good disease, but
We doing that in this.
yeah, not good. So you have 1 in 7,000 have this, so 1 in 7,000, what is that? 1 in 7,000. What do we call that?
That's the
It's a fraction, but what is it called? What are we calling it?
The frequency.
That's good. Frequency. Love it. Love it. Frequency of
Something.
little c, right? Which is equal to what? The frequency of the recessive allele. How do I know that it's the frequency of little c? They didn't say little c. They said cystic
Yeah, that's
fibrosis.
why I said something. How did you find that out?
Because what? What they told you, little cystic fibrosis is recessive.
Oh, yeah.
So that means it has to be little c. So this tells you it's the frequency of little c, which is what? In our equation is what?
The recessive, what you asked?
Q, no, Q squared. It's Q squared.
Oh, yeah, because there's 2 C's on here.
There's 2 C's. I keep telling you, it's kind of a thought process here. You see 2 C's, then you should be thinking squared, all right? All right, so Q squared is 1 in 7,000.
That's a very small.
What's the 7,000 business? What's 7,000?
That's the total population.
That's the total population we're considering.
no, it's 1 in 1,700.
Huh? What did you say, girl?
It's 1,700, not 7,000.
Oh, sorry,
Oh, it is 1,000.
I misread that.
I was
I'm glad
gonna
you
say,
caught
that's
that.
a big number.
So 1,700 is the total population. And this shouldn't be this should be 1 in 1,700. Okay?
Yeah.
Thank you for catching that mistake. Are we clear on what's going on here?
Yeah.
What's interesting to me is on a Saturday, we're still having people having side conversations, and I'm literally trying to work you through this, and I don't have time to go back. And there's going to be people leaving here saying, I just don't understand, blah, blah, blah. And come on, guys. All right. So that's Q squared. Does anybody have a question about that? Well, how we got that? What information there was in the problem that got me there? Is there anything confusion about this? Because that's Hardy-Weinberg. This should be Hardy-Weinberg should be an easy 250 points for you on Monday, right? Easy 250 points. You should be like, thank God I got Hardy-Weinberg. Yay, this is easy.
No.
All right.
You know how it says Caucasian, you don't incorporate that anyhow into the problem?
No, this is just, it says Caucasian, that just happens to be the problem they're looking at.
Okay.
Just the population. I mean, you might have to, depends on the questions they ask. The next question is, what percentage of the above population has cystic fibrosis? Well, how do you find percentage? Divide. So guys, we need to focus. I'm gonna say, I can't say it anymore. 1 divided by 1,700 is what? Well, I'll tell you, it's 0.0006. I'm gonna round it out to 6. So, what percentage is that?
Can you make that bigger?
What percentage is that?
The yellow.
0.06%. 0.06%. So not even 1% of the population. By the way, you want it bigger, like this?
Yeah. No, I was talking about the yellow. Can you just...
Like that?
No, I just need you to make it, enlarge it.
I can't, I don't want to get into separating it. Yeah.
So when you move the decimal back, when you try to stick it like, keep it like put it back on the side, on the other side of the stick.
So the easiest way to do it is to think, if you're going from decimal to percentage, you're moving it twice to the right. Just twice. So you don't move it on this side of the 6 yet, because you're not ever going to do that. I mean, unless you have 0.06, right? Anything you got, if you're going to move it into, if any decimal you have that you're moving to percentage, you move the decimal twice to the right. That's it. If you're going from percentage to decimal, you move it twice to the left. Now, dividing it gives you the decimal, all right? But to find the percent, you have to move that decimal twice to the right. To the right. Yeah.
So if you take the whole population and all the big C's and big C, and big C, little c, and then you kill off all the little c, can't that population still get cystic fibrosis from just having big C, little c?
Yeah.
Yeah, you have carriers. So carriers an issue. That's why recessive diseases stay in the population for so long. And it's also one of the problems with incest when we have a lot of inbreeding in small populations, what we call founder effects. When we have populations in the old days that would land on an island, and you have a small group of people, maybe there's 15, 20, 60 people in the group, and they land on an island, that's the genes you have. And so if you have recessive genes, they're going to come out, because over time, you're going to have a lot of inbreeding, right? It's not necessarily incest. All right, so that's it. All right, so bottom line, it's a little bit off topic, but it's interesting. But cystic fibrosis, we got Q squared is 0.06% of the population. So what does that mean? That means little c is 0.06% of the population. How are we going to find, though, if you think about it, how are you going to find the number of, can you find the number of little c alleles in the population? How do you find that?
So you take square root of the first?
No.
No.
Little c. No to him. I don't know about you, Lipscomb. What'd you say?
It's probably wrong. It's okay.
No, go ahead, say it.
I said
Yes, you're right. See, I would say no to him, because I don't want to say people's names, but I'll go ahead and say it. Derek made a good guess, but it was wrong, and you made a good statement, you're right. So remember, Q is how many little c's singular you have in a gene pool. And to find Q, when you have Q squared, what are you going to do? You take the square root. 0.0006, the square root of that is equal to 0.025. Now, this is something that amazes people all the time, and sometimes I would say it confuses people. When you take the square root of a decimal, it turns out that the answer is bigger. All right. So, and when you take the square of a decimal, guess what? It gets smaller. That's just the way it is, and it makes sense. I'm not going to get into it. Mathematically, it makes sense, but you need to get used to that, right? Some people get freaked out because the number looks bigger, and they're like, "Does that make sense?" It does make sense. Yeah.
So when you put this into that P plus Q thing to get P.
All right, good. See, she's thinking ahead. She's thinking ahead. So she's tired of all this game plan. She wants to get moving on this. So Q equals 0.025. What does that mean?
It means that, that's all of the little c's,
That's all the little c's.
period.
All the little c's were what?
Q squared.
Q squared, which is up here. That was 0.006. Q right here, Q squared, 0.0006. It was all the little c's, okay? To find just the little c, this was the little c. This is now what? The little c's. Does that make sense?
Okay. Well,
So the frequency, not the number. This is another big issue. The equations won't make sense unless you think of this as frequencies.
I'll rephrase it.
All right, so I want you to make sure, because this is a big problem. Because intellectually, as your brain is trying to figure this stuff out, the problem does not make sense at all if you think that we're talking about 0.025 equals the number of little c's.
Right.
No, it's the frequency. How often do you find a little c? We could not. All right, so that's it. So yeah.
Never mind.
All right, so little c, and little c equals the q, and little c equals q squared.
Right.
Now that you have q, now it's easy to find p, because if you have 2.5%, notice I looked at this number and my brain automatically saw what?
That the decimal move over
Oh,
twice.
it went great.
It's fake, yeah.
It's faded, yeah. There's sunlight shining on there. I can't.
And it's already
Because we
yellow.
can see the light.
It's yellow.
Really
You know what? I'll increase the size of the markers, so that should increase.
It's either really skinny or it's
Yeah, it's really skinny and it's fading out. What we're saying is that if you have this total population, do you see that better? Okay, if you have this total population and 2% of the population, just 2% of the population of all, and not population, excuse me, of all the alleles in the population. So alleles means either you got big C or little c, right? So all the alleles in the population, 2.5%. Did you see how automatically I see 0.025? I automatically think 2.5%?
right.
Because it's just in my mind, I moved the decimal two places. You got to be able to do that. You got to be able to look at a decimal and say, okay, you know what, that's 2.5%. Or a lot of this, you might get easily confused. So if 2.5% of the population is little c, what percentage is big C? 97.5, is that right? I didn't do the math.
Yes, it's 97.5.
So 97.5% is what?
The rest.
Big C, right? That's where this equation comes from. P plus Q equals 1 is simply that this whole pi equals 1. If 2.5% is 1, then the other one has to be 97.5. I mean, that's it. That's it. I mean, it makes sense, right? So that's all there is to it. That's where you get this equation. It gets more complicated when you have 3 genes, or 3 alleles, or 4 alleles, or whatever.
Randall,
Yeah,
can you explain that over there?
what?
It's like, I can't see it for you.
What are you talking about? The stuff we already covered? Let's just go on and we'll do another problem.
You
And
don't
so,
have to take the square root of that number, right? Or the 97.
well, no, you don't have to take the square root of that number, because what you did is you looked at this equation here. You see, there's no square, are they?
No,
Are there
I'm
no?
talking about before when you squared the cube.
Well, we squared the q here. We had the q squared is what we found. That was given to us. They gave us q squared when they told us that little c
We had to
c
find Q.
was 1 out of 1,700, which gave us this number. They told us little c. So we had to know that was q squared, you see. Now, that's why we had to take the square root, because it gave us a square. But once we found the q, then we could use this logic here, right? To say if we got 2.5% of these, then 97.5% has to be big C.
So now can you find how many people in the house and how many?
Well, not yet, because we don't have all the allelic frequencies. The only allelic frequency we have is this one, right? All we got is little c. We know little c equals q squared, which equals 0.0006. We know that. We still don't know what big C little c is, or big C is. Now, big C is p squared, right? So that's easy to find out. Why is it easy? Because we figured it out up here, you see. So this is p right here. So what's 0.975 squared? Somebody want to do the math? Do you want me to do? 0.975 squared. So 0.975 squared is, well, I got 0.95. Should I do it again?
No, it's right.
0.975 squared is 0.95. So that's 0.95. Now look, some people are going to say, wait a minute, that doesn't make sense. You had 0.975, now you're squaring it, and now you're making it smaller, right? People freak out over this. They think there's something wrong. And I don't blame them. Because you think you're squaring something, you're taking one thing and multiplying times another, it should get bigger. That's true of things that are not decimals. So whole numbers, that's true. If you have 2 and you square it, that's 4. It's going to be bigger, right? 5, you square it, that's 25. It gets bigger. But decimals, when you square them, they get smaller. So don't freak out over that, okay? So there's your c squared, there's your p squared. Now, what are we going to do with this one? See the heterozygote. We're going to do what? What's the formula for the heterozygote?
2PQ.
2pq, which equals 2 times 0.975 times 0.0006. All right. Anytime you multiply decimals, they're going to get smaller, so you don't freak out. And by the way, it should make sense to you a little bit, shouldn't it?
Yeah.
If I take 0.5 and I multiply it times 2, doesn't it get smaller? Doesn't it get smaller? Yeah. So you kind of it's has to make sense to you on some level. All right. So, anyways, when I take that, someone do the math already, or should I do it? 2 times 0.975 times 0.0006 equals, I don't know if somebody else did it to check it, but I got 0.00117. That's what I got. And if I'm thinking, I think automatically my brain goes, look, I got 0.12%. That's 0.12%, right? This is 95%, this is 0.12%, this is 0.06%. That's what I see. And all three of these added together should equal 1, right? So that's another way you can check it. 0.0017 plus 0.95 plus 0.0006 should equal 1. And I got it equaling 0.95177. So, and my guess is that the reason that is that we have rounding errors. But are we good? So that's what we're dealing with. Is everybody okay with that?
0.001.
So what did we find here? What did we find? What was this? This was what? Allelic or genotypic? Genotypic. You see these squares, you're thinking genotypic frequencies. If you see the P and the Q, then you're talking allelic frequency, how many alleles in the population. And someone keeps asking, well, now can we find how many? If I told you there were 1,000, what if I told you right now that there was 325, I'm just making up a number, 325 million people in the United States. How many people have cystic fibrosis? How many would you expect to have cystic fibrosis? 320, do it, someone do it, 325 million, do it, give me the number, I'll do the number too. 325 million people, how many people do you think are gonna have, how many people do you think are probably gonna have, how many would you expect to have cystic fibrosis?
0.006 times 325, 195,000.
That's the number I got, 195,000. So I expect 195,000 people to have cystic fibrosis. Now, you thought this number was small, didn't you?
Yep.
But then you think about how many people that means out of a big population. That's a lot of people with cystic fibrosis. Now you go ahead and you do the math with how many people are carriers. How many people carry out of that 325 million? How many people carry the gene for cystic fibrosis? So you should be able to do that. And that is 380,250 people. So altogether, about 500,000 people are involved with cystic fibrosis out there.
That's crazy.
Right? That's a lot of people. It's a small percentage of the population, but it's a lot of people. All right. So when you're thinking of these numbers, you have to think the grand scale. And if you think about it worldwide, it's kind of hard to do that with genes because you have different populations in the world. But if you just think about it just as a human population, just worldwide, you take that same percentage and multiply it times 1 trillion people. Now you got, because that's about what the population is going to be in a few years, about 1 trillion. That's a lot, yeah. And so, I mean, can you imagine how many people are going to have cystic fibrosis and what kind of issues you're going to have with that? All right, so let's move forward. Let's do number 8, or do you want to go and do another sickle cell? You should be able to do the sickle cell one in your sleep by now. We've done so much with it. But number 7 says, in 9% of African American population is born with severe form of sickle cell anemia. What does that severe form mean? What does that mean?
They have it, but it's still.
They have what?
Sickle cell.
They have the disease, right? What does that mean? Little s. They have the
That's
disease.
2 squared.
So the 9%, they give you a phenotype, but that automatically gives you a genotype for the recessive only. You cannot find P with just Q squared. You have to do some math. So that's Q squared. As soon as you see that Q squared, you should be thinking, if you want to find Q, I got to be thinking the square root, right? All right, so what percentage, and they even tell you little s, okay? What percentage of the population will be resistant to malaria because they are heterozygote? So now they're asking you, what's the heterozygote? So they're asking you for the genotypic frequency of the heterozygote when they're giving you the homozygous frequency. How are we going to find that? What's the first step?
Well,
Come on, we just did it.
find Q.
Find Q. So I got Q squared, which is equal to, what was it?
0.09.
Nice. She did the math already in her head. You see that? 0.09. They told her 9%, but she automatically knew that she had to get that in decimal form. Now 0.09, you take the square root of both sides. And what do you get? Q equals what? What is it? I can't hear because someone's talking. 0.3. So 0.30 is your Q. Now you got your Q, what can you figure out? Remember that whole deal with the whole allele. Now we have the allele frequency for the small, the recessive one. So again,
The dominant one is.
if you have about something like this, a slice of the pie that's 0.3, so easily what's the rest?
0.7.
0.7. right?
Yeah.
So if 30% is recessive, then the dominant allele must be, so this is P over here, and this is Q over here.
Don't you put that in to get the, what is the heterozygous?
That's right, you got
Yeah,
it.
cause you know what it is for one.
That's right, so what formula do you need to know for heterozygous? What's the heterozygous one? No, you don't, you're right, you're right, that if you wanted a dominant, you would use P squared, so you're right. 2PQ, so just use 2PQ, that's it. And that's the heterozygous, that would be big S, little s. And 2PQ is equal to 2 times 0.7 times 0.3, right? And that equals what? Somebody know the number there? Do you see how easy this is? This is real easy. Once you got the little basics, it's, what is it?
42.
42%, so 0.42 or 42%. All right, so this is actually, Hardy Weinberg is kind of one of those things that's, okay, great, I got it, let's do it. But they could ask you some really weird questions on it, though, that's the problem. All right, do we have Hardy Weinberg pretty well done? We don't have to do any more with these. The practice problems, I mean, yeah. Let's go on to chi-square, what do you guys think? We're good?
I'm good.
Huh? Yeah, I'll post it. I also post the chi-square stuff we started yesterday too. I didn't post that.
So, the question we're gonna have on Monday, you said it's gonna be like 15 step. Is it gonna be like the one where we have to fill out the
It's gonna be exactly like your lab.
Like,
All right. So your problem on Tuesday, on Monday's quiz, is gonna be just like number 12.
so it's like,
I'm gonna change the numbers. And I'm gonna let you do the rest.
so like we gotta fill out the hybrid cross.
You have to do dihybrid cross. You're gonna have to figure out what the observed are, what the expected are, what's the observed minus expected. Then you have to find chi-square. Then I will give you the table, and you'll have to figure out what your critical value is based on your degrees of freedom, and you're gonna assume 0.05 for P. Are we good with that?
Yeah,
Do you want me to do it?
I'm good with
You want me to do one? And we'll go for chi-square? All right. If people are leaving, let's give everybody a minute to leave, sign out, and then we're going to go ahead and do chi-square.